It all started with light, smart light. Then it quickly spread to rocks and other projectiles. Now it's seemingly everywhere. But before I tell you about that, consider how smart people react to certain situations. If I have a trial where you have to start at point A and run and touch any point on the wall, and then run to point B, how do you decide what is the quickest path to take? And how do you decide where to touch the wall? You could run to here, or here, or here. But after a moment, you pick this point because you think it's the shortest path and results in the quickest journey. In a second trial, you are a lifeguard and you spot a swimmer in trouble out in the water. How do you decide the quickest path to the swimmer? You run faster than you can swim. So do you run to this point and swim from there? Or maybe this point? If you choose correctly, your path will be the path of minimum time, and you will have joined the ranks with Fermat, Maupertuis, Euler, and Lagrange in furthering one of the most universal principles of nature. Living in the first half of the 17th century, Pierre Fermat developed the concept that light travels at different speeds in different media, and maintained that the path the light takes is always the one that takes the least time. His detractors at the time gleefully pointed out the obvious objection. How does the light know which path will be the quickest? Smart light? Pierre-Louis de Maupertuis, the son of a wealthy pirate, expanded Fermat's least time idea. He wrote that in all events in nature, there is a certain quantity called action, which is always a minimum. His good friend and mathematician, Leonard Euler, added the idea of conservation of energy and made least action an exact dynamical theorem with this mathematical form. Euler also developed an ingenious graphical method to find the path of minimum action for a system. Another young scientist of the time, Joseph-Louis Lagrange, eagerly applied these ideas to the tantochrome problem. This is the problem of finding a curved shape on which a weight started at any point on the curve will slide to the bottom in the same amount of time regardless of its starting point on the curve. He expanded the idea of action to be the function of kinetic energy minus the potential energy. This is proven to be a much more universal formulation. Now that we know all of this, let's throw a smart baseball straight up with enough force that it returns to our outstretched hand 3 seconds later. And let's see if we can discover its motion using the principle of least action. When we first throw it, it has a lot of kinetic energy, and its speed is at a maximum. But gravity slows it down as it rises. At its peak, its speed is 0, and all of its energy has been transformed to potential energy. On the downward trip, all the potential energy gets reconverted into kinetic energy. Its kinetic energy is related to its speed, and its potential energy is related to its height. Now on this graph, we have the baseball's height on the y-axis and the time on the horizontal axis. To begin, we have divided the 3 seconds of flight time into a few time intervals. As we adjust the height of each point, the computer will calculate the total actions for us. Remember, we are looking at the minimum actions possible while keeping the ball in the air for 3 seconds. The height of the dot is directly related to the potential energy, and the slope of the line gives the speed, which is related to the kinetic energy. The steeper the slope, the faster the baseball is moving. As you can see, it is an iterative process. It will take several cycles before we can no longer make the total actions any lower. That is, less negative. Here's the same problem with more sections in the graph. To do this perfectly, the number of sections must go toward infinity, and the width of each section must go towards 0. But this approximation with 40 sections is good enough to show all the features. Now that we have the motion, let's examine the path, or world line, and see what we can see about how smart that baseball really is. The numbers to the right list the change in velocity for each segment, as well as the acceleration for each segment. You can see that the change in velocity is constant from section to section, and the acceleration is equal to the standard value for the acceleration of gravity, 9.8 meters per second squared. Since we are on a roll, let's do it one more time, showing for each section the kinetic energy, the potential energy, the difference between the two, as well as the total energy. Adding the t minus v column gives the total action, which is smaller on the path than any other possible path. You can also see that the total energy is constant, as it must be if energy is conserved. And to demonstrate how versatile this baseball is, let's throw it onto the roof of a house, so the endpoint is 4 meters higher than the initial point. Method still works pretty well. Smart baseball. While everyone has heard of Isaac Newton and force equals mass times acceleration, it is this other equivalent formulation of kinematics that is more versatile and has direct extensions into relativity and quantum mechanics. So, how does the light know which path to take to satisfy the principle of least action? Richard Feynman gave us the answer, and we will explore that answer in another video on QED.